Hi everyone. So even though self-driving labs are a new emerging field, there have been already many studies and very interesting works and reviews on it. One work that really caught my attention was this paper by Florian and Alon's group. Their method, which is called Clarify, automates chemistry experiments by converting natural language instructions into executable robot plans using LLMs, and also it helps with task and motion planning. So looking at the reviews, looks like the current challenges in like self-driving labs can be categorized into motor function and cognitive processes. So my work, based on my background, will be mostly focused on cognitive processes, but I would definitely love to learn more on the robotic side of things as well. So let's briefly talk about motor function here. Motor function refers to the mechanical aspects of the lab's operation, like how robots can handle and manipulate objects, transfer liquids, operate instruments, and perform other tasks that typically require humans to perform them, given our great skills and hand-eye coordination. Now, on the other hand, we have the cognitive processes, which are about decision making of human scientists, like interpreting experimental data, making predictions based on past results, designing experiments, and adjusting protocols based on the current state of the environment or like dynamically. So, if I were to make an example, Clarify is like a great example on integrating these two categories together. But when it comes to handling like dynamic exceptions, there are some limitations. One example, which is actually defined as a wrong action in the Clarify paper, is reusing beakers or vessels before they have been cleaned. There's also the limitation of handling out of context chemistry related information. So, by out of context here, I mean information that are not necessarily provided to the LLM as a natural language input. So, as an example, this would be experiment descriptions that include conditional statements like heat the solution at the boiling point until it becomes white. One issue is that we don't provide the exact information on what exactly the boiling point temperature is, and this is like vague description. We're going to be looking at this example later. I feel like there is a great opportunity to incorporate more chemistry domain knowledge, automation, and real world experiments to the system. And all this can be automated through an AI agent. Alright, let's go back to the example I just made earlier. Consider this input prompt as natural language input, where the AI agent is tasked to heat up methanol up to its boiling point, check for health hazards of the compound, and stop the experiment if unsafe. And we also added an experimental constraint here where we have no fume hood available. So it's a common setting that might happen in a real world scenario. Our AI agent here is equipped with a set of tools that can provide it with guidance on how to autonomously do experiments, post-process experimental results, consider safety constraints for each part of the experiments, and also dynamically adjust its planning. What's important here is that we also have a tool that can incorporate physics-informed or chemistry-informed knowledge into the decision-making and plannings of the agent. Now, the chemistry-informed knowledge can be coming from various resources such as internet, online databases like PubChem, Materials Project, or even like scientific research articles coming from different journals. And all this is done through React that allows us to have the synergy between chain of thought reasoning and action. So when I say reasoning, what I mean is that the LLM can formulate a plan of action, as in make a decision. And action means that the LLM can interact with external sources such as knowledge bases or environments to gather additional information. So I would like to take a moment and highlight the word flexible in this setting. What I mean by flexible is that this approach can be applied to all 6 driving labs at AC or any other lab with minor changes. Because when it comes to interacting with robots, it's just a matter of defining a Python wrapper around whatever API the robot uses to run and have that work with the agent. Alright, now let's look at some preliminary results on this and how a system like this can work. So I've developed some code that will actually use this exact example. The code is publicly available on GitHub and we're gonna go through it real quick. If you have any questions, I would be happy to discuss it with you. So here I'm actually using LangChain, a Python package that allows you to develop applications with large language models. What's nice about LangChain is that you can actually develop tools as Python-based functions. And these tools are essentially a way of turning human domain knowledge into an algorithmic format that can be used by the LLM. Here, we use one tool only to our agent that is powered by GPT-4, and that tool gives it access to PubChem so it can look up a compound and find its property if the agent does not have this information. So back to the example that we had, this is the input prompt you're using, and we only have this input prompt and also have the information on the tool that is access to PubChem. Now, I would like to go through the results with you, and what's exciting about LangChain is that you can actually see the chain of thought reasoning on why the agent made a decision, for instance. So we go line by line here. The agent is going through the prompt we inputted, where it's asked to heat up methanol up to its boiling point, and also find the safety hazards about this task. So the agent is actually like, I don't know the exact boiling point of methanol. This information was not provided. I also don't know the health hazards to this. So maybe I use the tool I have to find more information. And it actually uses our tool, goes to PubChem, finds out the boiling point of methanol. It also finds the information on the health hazards for methanol. And based on these two, it makes a final decision. And what's exciting is that apart from the information about like the boiling point and the health hazard, it is saying that here, it is saying that given these health hazard, maybe it's not safe to conduct this experiment considering that you don't have a fume hood available. So you can consider better safety measures, and after that you can do the experiment. So this is like a great example of how you can use an agent like this for developing a self-driving lab. And this is just for like illustrative purposes. You can obviously have the output be in a structured format for like implementation purposes, have it outputted as a JSON, or you can actually develop other tools. So here we only obtain information from PubChem, but you can actually easily develop retrieval augmenting information from like the material safety data sheets of the compounds using semantic similarity search, or you can do much more complex things, as in incorporating visual feedback from the environment. So you would, for instance, obtain an image from the environment and use GPT-4 vision to actually handle multimodal input here and process that image and solve problems like acid-base titration, or back to the original problem I was discussing, heat up the solution until it becomes white. So that color change is also something that we can possibly solve. Now that we've seen this example, let's look at possible problems that we might face developing AI agents. So the first problem is actually not necessarily specific to an AI agent, but the nature of large language models and how they do not perform really well on domain-specific tasks because they do not have the specific training data so that they can perform that task well. So if I were to make an example, in the Clarify paper, the robots gets their commands through a domain-specific language called XDL. And XDL is not necessarily as available as like Pythonic code. Therefore, like the expectation of the LLM to generate perfect XDL code is not reasonable. So the way you can handle this is that you can actually develop a tool that essentially guides the LLM to generate XDL code in a systematic way. This is one solution. Another solution would be fine-tuning, of course. The next problem comes in when you want to, for instance, develop a multimodal agent that can process visual feedback from the environment. And if we actually want to use this in real time, this might be problematic given the slow response time from OpenAI servers, but things are moving really fast. So I think this will be a problem that this is a problem that's going to be fixed soon. In the worst case scenario, you can not necessarily use like GPT models from OpenAI, but use other large language models and run them locally on a computer that has good GPU. And finally, when you're developing an AI agent, of course, in the example I made, we only have one tool, and that was just to look up PubChem. But what happens when you have a lot of agents? So this is something that could be misleading to an AI agent, which tool exactly to use and how they can prioritize the tools they have, which is something interesting because just recently, like the idea of super agents was discussed on Twitter, where we actually have not one but few agents that work with a super agent. So this is like a nested AI agent where we can actually have different AI agents complete different tasks, as in one would handle robot high throughput experimentation, one would handle liquid sample handling, one would be in charge of safety, another one would be in charge of like chemistry informed knowledge, and these would interact all together. So that is all I've prepared. I really look forward to our discussions on this. Thank you for your attention.